So ladies and gentlemen, we are still dealing with acids and bases. Chapter 14 was the kind of the essentials of what we needed for acids and bases. And chapter 15 is really the heart and soul of what we can do with acids and bases. So chapter 15 is entitled The Application of Acids and Bases. The first thing we're going to look at is something called the common ion effect. So the first thing I would like you to do is write the equation for acetic acid in water. And this is one of the possible choices that you could write for acetic acid in water. This is one way to write acetic acid. This is the other possible way to write acetic acid. So either one of those would have been acceptable to write acetic acid in water. Okay, so I wasn't sure which one you'd write, so I wrote both. But I'm actually going to deal with this particular one. And what I'd like you to do now is answer the question, what do you think would happen if sodium acetate were added to the solution? So this is the previous solution. I want to add sodium acetate to this one. What do you think would happen? And what you should realize is that, first of all, this sodium ion doesn't matter. So essentially what we're doing is we are increasing the concentration of the acetate ion. So if I am making this ion go up, this should trigger into your thoughts Le Chatelier's principle. And if that goes up, then this concentration should go down. And that should, by default, go up, even though it won't matter. But that concentration would go up anyway, or also, and that results in a shift of this equation to the left. But now you need to think of the consequences of that. If this concentration, if our H3O plus concentration goes down, okay, so that goes down. What just happened to the pH of the solution? And it's kind of counterintuitive, but the pH of the solution would have increased then. And all this is a Le Chatelier shift, but it's actually referred to as the common ion effect. Do not write this definition down. This is the technical definition of the common ion effect. And why they made it so wordy is beyond me. But this is the exact definition, and you can read it. This is the definition I actually want you to write down for the common ion effect. Basically, if you have an ion in common with the reaction will shift to relieve the stress. All the common ion effect is, ladies and gentlemen, is Le Chatelier's principle. It's nothing more than that. So this definition is beyond me why I had to try to make it so scientific. Okay, so let's say I have the compound HF, okay, nice little weak acid, and I put HF into water. Since it's a weak acid, it's going to go into equilibrium, so write the products of that. And you would get H3O plus and F minus, okay? Now, let's say I add to this solution a sodium fluoride solution. So I'm going to add sodium fluoride to that solution. Again, sodium doesn't matter because there's nothing in common to the equation with sodium, but essentially what we're doing is increasing that concentration. So again, what we would do is we would shift this to the left. So this right here is the common ion that's coming from NaF. And again, you need to consider if that's shifting left, then H3O is decreasing. So there's a decrease in the hydronium ion concentration, which means there's an increase in the pH. stop and process that a little bit. That's an important process to make. If I decrease H3O, the pH increases. So, what we're going to do is we're just going to look at this, but we're going to look at this in a couple of steps. So this is not a common ion effect problem at this point. I just want to calculate what the pH of a 0.3 molar acetic acid solution would look like. This is just our good old friend calculating the concentrate or the pH of a weak acid. So I have CH3COOH in water. That's going to give me H3O plus CH3COO minus. And all we're going to do is make an ice chart for this. This is 0.3, doesn't matter, 0, 0, minus X, 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 0.3 minus X, X, and X. Okay, so the Ka of this is going to equal X times X all over 0.3 minus X. And since Ka is 1.8 times 10 to the minus fifth, that's going to equal X squared all over 0.3 minus X. So you can see this is just an old weak acid problem. That's 10 to the minus fifth, so that X doesn't matter. And you can do the math on your own. I'm just going to quickly solve. The X turns out to be 0.002, and that will be molar. And X happens to be the H3O plus concentration of 0.002 molar. So putting that in, I get a pH of 2.69. Okay, nothing hard there, okay? But remember that pH of 2.69. Now, what I want to do is calculate what would be the pH of a solution if I have 0.3 molar acetic acid and 0.8 molar sodium acetate mixed together. Okay, now, what you need to recognize is that is our acid, and sodium acetate is our salt that we're going to add, okay? So the sodium in this sodium acetate, which by the way, the formula of sodium acetate is NaCH3COO. That's sodium acetate. The sodium doesn't matter. So that's going to leave us with the acetate ion. So the equation for this doesn't change any. It's still the equation for acetic acid in water. Oops. Okay, so that is still our equation. And we're still going to ice this. Water still doesn't matter. The only difference now is this is 0.3 molar to start with. This is 0 to start with. But because of this sodium acetate salt solution that we're putting in, this is 0.8 to start with. Okay? So that's going to actually cause our reaction then to shift this particular direction. So this is still minus X, this is still X, that's still plus X. So at equilibrium, this is 0.3 minus X, X, and this is 0.8 plus X. So our Ka expression now is X times 0.8 plus X all over 0.3 minus X. So Ka doesn't change. It's still 1.8 times 10 to the minus fifth. And that's going to equal x times 0.8 plus x all over 0.3 minus x. Okay? Now, we still have our 10 to the minus fifth issue here, so we're still good there. And that means I can cross out that x, but it also means I can cross out that x. So then, doing our normal algebra, which is multiply both sides by 0.3, which would get rid of that. So I'm going to multiply by 0.3, and then I'm going to divide by 0.8, which would get rid of that. So I'm going to divide this by 0.8. That is going to give me my value of x, which in this case, oh shoot, no. Never mind. Is going to give me sorry, I did not actually have that worked out. A value of 6.75 times 10 to the minus sixth molar. And again, from our chart, X is the H3O plus concentration. So my H3O plus concentration is 6.75 times 10 to the minus 6 molar. And then from that, we can calculate the pH, which is 5.17. So, one of the things that you'll see here is just what happened to the pH because I had this salt added. Without the salt added, going back to this problem, our pH was 2.69. So this was our pH without the salt. With the salt, our pH is 5.17. So you can see that what we did by adding the common ion is we shifted the reaction back to the left. And that is essentially the common ion effect. So I'm going to stop here and assign worksheet 1. And if you want to go look at worksheet 1, okay, I am going to create a second video, and I'll just jump ahead here, which will work through one more complete example, but it will be a second video, and you'll be able to watch it or not watch it if you understand. But this video is more like the worksheet that you're going to be dealing with. So if you don't understand the worksheet when you get to it, please watch this video, the second video.